Well, let's begin with next homework. Homework number 7. The assignment is to convert from polar coordinates r and theta to Cartesian coordinates x and y. We should use easy formulas. Delta x, or difference between xb and xa is equal to r cosinus theta, and delta y, difference of y coordinates, is equal to distance, r distance, on sinus theta, or sinus alpha. In any case, the assignment is very easy. In Ukrainian, we use the name for this assignment, direct geodetic assignment, direct geodetic task. I am not sure that we have a similar name for this task in English. However, direct geodetic task. So I will show you how can we calculate coordinates of second point B or second point 2. The yellow cells in the table is the result. So, for example, we can use the variant 20. The first step is to calculate azimuth in radians. Well, we type and radians. Sorry, my Excel has Russian interface, so he need to put equations in Russian. Radians of azimuth enter. So the first step is calculating of the value of the angle, azimuth angle in radians. Next step, we calculate the function cosinus of the angle in radians. Next step, we calculate the sinus function of angle in radians. Then we use the formula for delta x or x differences, the catet of this triangle. This catet of this triangle. We just need to use this formula. The radial distance 105 meters to the cosinus. It is 70 meters point 26. Then we use another formula for delta y, 78 meters. And the last step is calculating of Cartesian coordinates of point 2, point B in this picture. We just need to x1 coordinates plus difference of coordinates, enter, and y coordinate of first point plus difference of coordinates. We have got these coordinates. So you can see the variant 20 is done. So if anybody have questions, please. If you have no questions, we will continue with our lectures. Please type down plus in the chat if you have understood the assignment. Let's move on. Today we will speak about leveling. Can you see my screen?
Yes.
Well, leveling. In this picture, we can repeat all the main terms that are connected with leveling. We have geoid that is that continuous mean sea level, and we have arithmetic height above geoid. While we use global satellite system, we can calculate ellipsoid height. And so we should understand the difference between arithmetic heights and ellipsoid heights. Our lecture will consist of a few chapters. Structure of levels, adjustment of levels, error sources, procedure of leveling, line leveling, detail point leveling, and processing leveling data. Well, leveling is a determination of the elevation of a point or difference between point referenced to some datum. Datum are level surface to which elevations are referenced. The main datum is mean sea level, or MSL, the average height of the surface of the sea for all stages of the tide over some period of time. In different places we have used different zero levels. In this presentation you can see 26 tide stations along Pacific, Atlantic and Gulf, Mexican Gulf for the United States of America. Then these different vertical datums, we can choose one. For example, National Geodetic Vertical Datum. It's a national-wide reference surface for elevations throughout the United States, made available by National Geodetic Survey, based on 1929 adjustment. Benchmark, a relatively permanent object bearing a marked point whose elevation above or below an adopted datum. You can see the goal with instrument. This instrument we should call a level instrument. We have, as you can see in the slide, we have small difference. British English, we should write down leveling with 2L or leveling with 1L, American English. So leveling is a branch of surveying, the object of which is to establish or verify or measure the height of specified points relative to a datum. It is widely used in geodesy and cartography to measure vertical position with respect to a vertical datum, and in construction to measure height difference of construction artifacts. Well, we have been spoken about different mean sea levels in different countries. So in the United States they use National Geodetic Vertical Datum of 1929. It has been used as a reference for extensive network of benchmarks, and all these benchmarks are periodically adjusted as to elevation. The level surface parallels the curvature of the Earth. It's a level line is a curved line, normal at all points to plumb line. Well, line of sight is only normal at point of instrument. You can see in the picture. A line with a sight distance of 1 mile using the Earth radius 3,859 mile, curvature change is 0.667 feet. Refraction of line of sight of level is downward by a small amount. What does it mean refraction? Refraction is an optical effect of line of sight has slightly changed its direction because of refraction. Refraction is caused by temperature differences while we are observe with our instrument and want to find out the level differences of some points. The combined curvature and refraction amounts for short distances are, you can see in the table, these values are small for most instances and can be neglected. Most common leveling instruments today is the automatic or self-leveling level. It has an internal compensator that automatically provides a horizontal line of sight and maintains this through gravity. For example, prism hanging on pendulum. We use differential leveling or spirit leveling, most common type today. It determines the difference in elevation using a horizontal line of sight and readings on graduated rod. Circuit must be closed on benchmark of origin or on benchmark of equal accuracy. The process consists of several steps. First, a reading on point of known elevation. BS reading plus BM elevation. H1, reading on point of unknown elevation, Fs, and then Hi minus Fs is equal to elevation of new point. We have always some different errors in leveling, and we can first of all systematic error, inclination of line of sight due to curvature of Earth and refraction, and I will explain these errors later in our presentation. Here you can see the tests. The 7 basic rules of differential leveling. Balance length should be not very big. Not the maximum length should be 100 meters. We should make sure that gun of telescope is level and pendulum free. Then we should turn through all BMs, give complete description of BMs and TBMs, have rod rocked, make sure turning points are solid, and close all circuits of BM or same degree of accuracy. Other random errors: incorrect rod reading, most common viewing foot number above and recording it. Parallax, having the X hair not properly focused, and heat waves limit shot lengths. Another option is closure error, difference in measured elevation, unknown elevation. We should speak about the closure error later. Now, we can work with so-called precise leveling. Precise leveling, accuracy obtained by quality of instruments and care taken in the field. High quality automatic levels are utilized. Level rods are equipped with a rod level rod shoe to allow better setting of benchmarks. Scale on rod is made of Invar steel, not affected by temperature, generally called Invar rod. I will show you the example of this Invar rod. It is not very cheap. Invar rod for geodesy. Here you can see examples of this Invar rod, and Invar is a special mixture of metals it consists of 64% of iron and 36% of nickel. English. You can see samples of this Invar, and the coefficient of thermal expansion of nickel iron allows the plotted here against the nickel percentage on a mass basis. You can see the minimum of the graph explains the optimal percent of each metal in this mixture. Well, let's move on. Reading either taken by optical micrometer or a process called three-wire leveling is used. All three wires are read and averaged. Optical micrometer line side deflected by turning micrometer screw to read subdivision on rod. Rod division is read as normal, and then fractional reading taken from micrometer screw. Those on normal rod readings are very precise. So nowadays we also use electronic levels. Well, the principle of leveling, you can see brown line is topography surface. We have 2 points on the Earth's surface, and blue dotted lines is the surfaces of equal gravity potential or equipotential surfaces. Then we need to measure delta heights between points A and B. Then we use normal lines to equipotential surfaces. These normal lines are plumb lines. Then we put our level instrument between these points. The telescope of our instrument is also normal to equipotential surface, and then we can read the numbers of rod on the point A and rod on the point B. The reading of the back rod, so-called LA, the reading on the rod B is LB, and then we must calculate the difference between LA and LB. However, the line of sight is not equal to the equipotential surface. While we put our instrument in between these points, and while the distance from our instrument to the back rod and to the front rod are equal, these deltas, delta A and delta B, is also equal. So the whole equation will be delta H, delta heights of line AB between A and B points are LA minus LB the delta A and the delta B with plus and minus disappears in this formula, and so we can use the simple formula. This spherical approximation equal distance to A and B. So delta difference of heights are as follows. Tiling level. The surveyor's level is consists of different parts. We have diaphragm, tiling screw. It change the direction of our telescope to stand the bubble in the bubble tube in the middle. Also we have circular bubble. It helps us to stand the axis of rotation of the instrument in vertical position, and precisely we stand the line of sight with the tiling screw. This is a tiling axis that allows us to change the direction of the sight axis. And also the instrument is connected to the tripod with 3 screws. Clamping screw to fix the telescope in one vertical plane, tangent screw, slow motion screw, to finally rotate the telescope along the vertical axis. Now to set the line of sight to be exactly horizontal. How to, more general, how to set anything to be exact horizontal. We use such kind of equipment as the bubble tube. The bubble tube has inside the tube big radius, and the bubble stands in the middle of the tube while the tube is exactly horizontal. This another type of level. It's circular bubble level. It helps us to when the level is horizontal, the bubble is in between the red circle, in the center of the glass. The radius determines the sensitivity of the bubble tube. In different equipment, we have different bubble tubes with different radiuses. When the radius of the bubble tube is big, R1, the bubble tube is very sensitive. While the radius is not very big, R2, the bubble tube is not very sensitive. When we use such kind of equipment, bubble tube for construction, bubble tube for construction workers, these bubble tubes these construction levels is not very precise because you can see the examples of this aluminum box beam level set. Well, this because this level have small radius, and this level is not very sensitive. Well, sensitivity, how much the bubble moves due to a given amount of inclination. While we use precise geodetic equipment, we should use more precise level. Here you can see a huge amount of rotation levels and so on. These rotation levels or laser levels, they can create horizontal and vertical planes for construction. Construction levels and geodetic. Optical level. In this case, the optical level is more precise. More sensitive. Because the bubble tube is more sensitive. We can determine this sensitivity using these formulas, and also in we have assignment for our students to each line on the scale of the bubble tube, while the bubble moves to the one point, it inclinates on a small alpha angle, and we can calculate this alpha angle using the simple rod and measuring the distance between the instrument and the rod. Another important option of the level instrument is Kepler type telescope. We have object, and we have virtual image of the object, and we can see this virtual image of the object using the telescope. And the object length is so we have different telescope tubes. Sometimes the telescope tube shows us the magnified and inverted image of the object. in the diaphragm of the instrument, we have crosshairs. We use the crosshairs to provide visible horizontal and vertical reference lines in the telescope.